Chapter 31 Maxwell's Equations and Electromagnetic Waves. The units will be covered in this chapter include changing electric fields produce magnetic fields, Ampere's law and displacement current, Gauss's law for magnetism, Maxwell's equations, production of electromagnetic waves and their speed derived from Maxwell's equations, light as an electromagnetic wave and the electromagnetic spectrum, measuring the speed of light, energy in electromagnetic waves, the Poynting vector, radiation pressure, radio and television, wireless communication. Section 1. Changing electric fields produce magnetic fields, Ampere's law and displacement current. Ampere's law relates the magnetic field around the current to the current through a surface. Here we have a current in a wire, current I in the wire from left to right. We have a closed path through which we are taking the integral for the Ampere's law, and we have two surfaces, surface 1 and surface 2 can be arbitrarily chosen. In order for Ampere's law to hold, it can't matter which surface we choose. But look at a charging capacitor. There is a current through surface 1, but none through surface 2. The current wire that we talked about in the previous slide, we had two surfaces over the closed path, surface 1 and surface 2. But if we have a capacitor, which are like two parallel charge plates, we will not expect any current, but for another surface, we will have some currents induced through that surface. Therefore, Ampere's law is modified to include the creation of a magnetic field by a changing electric field, the field between the plates of the capacitor in this example. So on the left-hand side, we have the integral over the closed loop of B.dl. And the right-hand side, we have mu naught time enclosed current. The extra term for the displacement, which is added to the previous Ampere's law, is mu naught times epsilon naught multiplied by the derivative of the electric flux over time. The second term in Ampere's law has the dimensions of a current after factoring out the mu naught, and is sometimes called the displacement current. So let's factor out mu naught. So we have I plus ID enclosed, and I sub d is the displacement current defined as epsilon naught times the derivative of electric flux over time. As an example, let's look at problem number 4 in the book. A 2200 nanofarad capacitor with circular parallel plates 2 cm in diameter is accumulating charge at the rate of 38 millicoulomb per second at some instant in time. What will be the induced magnetic field strength 10 cm radially outward from the center of the plates? B asks, what will be the value of the magnetic field after the capacitor is fully charged? For part A, we note that the current in the wire is the rate at which charge is accumulating on the plates, and also is the displacement current in the capacitor. So for part A, we have total current is the current at the accumulation of the charges on the plates, and also the displacement current in the capacitor. Because the location in the question is outside the capacitor, we have to use the expression for the magnetic field of a long wire with the wire location along the line connected to the centers of the two capacitor plates. So for the magnetic field of a wire, we have mu naught times I over 2 pi r naught over 4 pi multiplied by 2I divided by r Therefore, this quantity, mu naught over 4 pi, becomes 10 to the power minus 7 Tesla meter over ampere. Multiply by 2, multiply by the current is 38 times 10 to the power minus 3 amperes divided by 0.1 meter as the radius. And that gives out 7.6 times 10 to the power minus 8 Tesla, and this is the magnetic field. For part B, after the capacitor is fully charged, there is no current, therefore there is no magnetic field. So we have B is equal to 0 after the capacitor is fully charged. Section 2. Gauss's law for magnetism. Gauss's law relates the electric field on a closed surface to the net charge enclosed by that surface. The analogous law for magnetic fields is different, as there are no single magnetic point charges, or monopoles. Therefore, for the magnetic field, we have the integral over the closed surface of B dot dA is equal to 0. Section 3. Maxwell's equations. We now have a complete set of equations that describe electric and magnetic fields, called Maxwell's equations. In the absence of dielectric or magnetic materials, the first rule is given by the integral over the closed surface of E dot dA is equal to the enclosed charge Q divided by epsilon naught. For the magnetic field, the integral of magnetic field B dot dA over the closed surface is equal to 0 because there is no magnetic monopole. The integral of the electric field over the closed loop E dot dL is equal to minus d phi over dt. That's the rate of the changes in the magnetic flux over time. The last equation is for the integral of B magnetic field dot dl over the closed loop, and is equal to mu naught times I enclosed plus mu naught epsilon naught, the rate of changes in electric flux over time. Section 4. Production of electromagnetic waves. Since a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field, once sinusoidal fields are created, they can propagate on their own. These propagating fields are called electromagnetic waves. Oscillating charges will produce electromagnetic waves. So here we have a representation of an antenna. Two pieces of metal are connected to a battery. When the switch is on and the circuit is connected, negative and positive charge are accumulated on the two plates, which cause an electric field between these two charged plates, and also we will have a current into the plates, which cause a magnetic field. Close to the antenna, the fields are complicated and are called the near field. So here is a representation of the antenna with a oscillating voltage, sinusoidal voltage applied. Therefore, we will have oscillating current through the circuit and also oscillating magnetic and electric field produced and is propagating in the air. So when the current is facing up, the electric field direction is from the top plate to the lower plate, and the magnetic field is produced into the page. But when the direction of the current is the opposite for the oscillating electric potential, the direction of the magnetic and electric field will be altered, and therefore an electromagnetic wave propagating from the antenna into this direction. But far from the source, the waves are plane waves. So this is the shape of the electromagnetic wave, which is propagating from the antenna to the right, and this is the direction of the wave traveling from the antenna as a source to the right. As it's propagating at far distances, these lines of field can be considered as parallel flat lines, and we can consider it as a plane wave. The electric and magnetic waves are perpendicular to each other and to the direction of propagation. The blue arrows represent the oscillating magnetic field along z direction, and the red arrows indicate the oscillating electric field along y direction. These are perpendicular to each other and mutually perpendicular to the direction of propagation, which is along x direction in this example. Section 5. Electromagnetic waves and their speed derived from Maxwell's equation. In the absence of currents and charges, Maxwell's equations become the integral of E dot dA over the closed surface is equal to 0 because there's no enclosed charge. For the magnetic field, no matter of the charges or currents, always we have the integral of B dot dA over the closed surface is equal to 0. For the electric field, the integral of E dot dL over the closed loop is equal to minus the derivative of the magnetic flux over time. The integral of the magnetic field over the closed surface over the closed loop B dot dL is equal to mu naught epsilon naught, the derivative of electric flux over time. The figure here shows an electromagnetic wave of wavelengths lambda and frequency f, which is propagating from left to right. The electric and magnetic fields are given by the electric field. Only component it has is along y direction, EY. It's given by E naught, and it's oscillating sinusoidally with the E naught times sine of the quantity k dot x, kx minus omega t. For B magnetic field, we have only z component, B sub z, and is equal to B naught times sine of the quantity kx minus omega t, where k is the wave number, 2 pi over lambda, 2 pi over the wavelengths. Omega is the angular frequency and is equal to 2 pi times f, the frequency. And we have a relation between f and lambda. F multiplied by lambda is equal to omega divided by k, and is equal to v, the velocity of the electromagnetic wave. Applying Faraday's law to the rectangle of height delta y and width delta x in the previous figure gives a relationship between E and B. So we have partial derivative of electric field with respect to x direction is equal to negative of partial derivative of magnetic field with respect to time. Changes in the position of the electric field, spatial changes in the electric field is related to the temporal changes to the magnetic field. Similarly, we apply Maxwell's fourth equation to the rectangle of length delta z and width delta x, which gives partial derivative of magnetic field with respect to x direction, partial b partial x is equal to minus mu naught epsilon naught, partial derivative of electric field with respect to time, partial e partial t, which means that spatial changes of magnetic field is related to temporal changes in the electric field. Using these two equations and the equations for B and E as a function of time gives E over B, electric field divided by magnetic field magnitudes, is equal to V, the velocity of the wave. By substituting values, we have velocity v is equal to c, speed of light, that is equal to 1 over the square root of epsilon naught mu naught. In the previous relation, epsilon naught and mu naught are constants. Therefore, the magnitude of this speed is a constant. The speed of light, 3 times 10 to the power 8 meter per second, precisely equal to the measured speed of light. Okay, as an example, I look at problem number 12 in the book. How long should it take the voices of astronauts on the moon to reach the Earth? Explaining details. So here we assume the only significant time is the transit time from the Earth to the moon at the speed of light. We use the Earth to moon distance, but subtract the moon and Earth radii, since the astronaut and the receiver are on the surface of the two. So if this is the Earth, radius of Earth, and this is the moon, this is the radius of the moon, distance between the Earth and the moon is d. What we are looking for is little d, the distance between the surfaces of the two planets. So little d is equal to capital D minus RE plus R moon. D is equal to V times T, and we know the velocity is the speed of light, so time is equal to D minus RE plus R moon divided by the speed of light. So let's plug in the values. We have 384 times 10 to the power 6 meter is the distance from Earth to moon. The radius of Earth is 6.38 times 10 to the power 6 meter. The radius of moon 1.74 times 10 to the power 6 meter divided by 3 times 10 to the power 8 meter per second, and it simplifies as 1.25 seconds. So it takes 1.25 seconds to transmit some signal from the Earth to the moon. Section 6. Light as an electromagnetic wave and the electromagnetic spectrum. The frequency of an electromagnetic wave is related to its wavelengths and to the speed of light through the equation C. The speed of light equals lambda, the wavelength, multiplied by f, frequency of the electromagnetic wave. Electromagnetic waves can have any wavelength. We have given different names to different parts of the wavelength spectrum. So here we are looking at the wavelength spectrum. Lower frequency waves like the radio waves, the wavelengths are around meter size or kilometer. The wavelengths, the frequency is between 10 to the power 8 hertz. We have microwaves around 10 to the power 8 to 10 to the power 12 hertz. We have infrared. The wavelengths is 10 to the power minus 3, power minus 6-ish. We have the visible light, only a tiny portion of the spectrum. The wavelengths between 7.5 10 to the power minus 7 meter for the red light, all the way to blue and violet colors of the wavelengths 4 times 10 to the power minus 7 meter, or we simply say between 400 nanometer to 750 nanometer, which is the visible light spectrum. We have X-rays, we have ultraviolet, and gamma rays. Alright, let's solve problem number 20 in the book as an example. How long would it take a message sent as radio waves from Earth to reach Mars when Mars is either A, nearest Earth, and B, farthest from Earth? Assume that Mars and Earth are in the same plane and that their orbits around the Sun are circles, and Mars is 230 times 10 to the power 6 kilometers from the Sun. To solve this problem, we have to note that radio wave is a form of electromagnetic waves, and they travel with the speed of light. So delta D, distance, is equal to c, the speed of light, times delta t, the time it takes to travel the distance delta D. The distance is found from the radii of orbits For Mars, when nearest from the Earth, the radii should be subtracted. And when this at the farthest distance, the radii should be added. Therefore, for part A, we have delta t is equal to delta d divided by c. When it's the nearest, we have 230 times 10 to the power 9 meter minus 149.6 times 10 to the power 9 meter divided by 3 times 10 to the power 8 meter per second, which gives 268 second, which is almost 300 second, or 4 minutes. For part B, when the Earth is the farthest from the Mars, the radii should be added, and we have delta D divided by C is 230 times 10 to the power 9 meter plus 149.6 times 10 to the power 9 meter divided by 3 times 10 to the power 8 meter per second for the speed of light. And that is equal to 1265 second, almost 1300 second, is equal to 21 minutes. That means when the signal is sent from Mars, it takes between 4 to 21 minutes to receive a signal from Mars to the Earth, or vice versa. Section 7. Measuring the speed of light. The speed of light was known to be very large, although careful studies of the orbits of Jupiter's moons showed that it is finite. One important measurement by Michelson used a rotating mirror. So here's the setup for the Michelson experiment. We have a light source which emits light, and it bounces off from a rotating mirror, goes to a stationary mirror, reflects off from there, reflected of the 8-sided rotating mirror, and goes to an observer. Over the years, measurements of the speed of light have become more and more precise. Now the speed of light is defined to be c equals 2.99792458 times 10 to the power 8 meter per second. This is then used to define the standard meter. To know more about the Michelson experiment, let's look at problem number 24 in the book as an example. A student wants to scale down Michelson's light speed experiment to a size that will fit in one room. An 8-sided mirror is available, and the stationary mirror can be mounted 16 meters from the rotating mirror. If the arrangement is otherwise, as shown in figure 31.14, at what minimum rate would the mirror have to rotate? Does this seem feasible? The mirror must rotate at least 1/8 revolution in the time it takes the light beam to travel twice the length of the room. So we say T is equal to 2 times the length of the room, we said 16 meters, and we need the speed of light 3 times 10 to the power 8 meters per second. And it takes 1.067 times 10 to the power -7 seconds. And we need the 8-sided mirror to be rotated at the angular frequency of 1/8 the revolution time it takes the light to travel twice the length of the room. So we say 1/8 time revolution divided by 1.067 times 10 to the power -7 seconds. That gives us 1.2 times 10 to the power 6 revolution per second. This frequency in the order of megahertz, the maximum ultracentrifuges that we can reach is about 150,000 RPM or 250 revolution per second, which is 500 times smaller than the value required to rotate this 8-sided mirror. So I would say this rotation rate is not visible. Section 8. Energy in electromagnetic waves. The Poynting vector. Energy is stored in both electric and magnetic fields, giving the total energy density of an electromagnetic wave, U, equals U sub E, density of electric energy, plus U sub B, the density of the magnetic energy. It is equal to 1/2 epsilon naught E squared plus 1/2 B squared divided by mu. Each field contributes half the total energy density. So U is equal to 1/2 epsilon naught E squared plus 1/2 epsilon naught mu naught divided by mu naught E squared, and it's equal to epsilon naught E squared. So 1/2 of the energy is electric, 1/2 of the energy is magnetic. The total will add up to epsilon naught E squared. This energy is transported by the waves, as we talked about earlier. So we have oscillating magnetic and electric field perpendicular to each other, and they're traveling at the speed of light. So this electromagnetic wave is transporting energy. The energy transported through a unit area per unit time is called the intensity. S, the intensity, is equal to 1 over area A times the rate of changes of the electromagnetic energy over time. So we have 1 over A du over dt, and that is equal to epsilon naught speed of light c multiplied by E squared. Its vector form is the Poynting vector S. Poynting vector S is equal to 1 over mu naught multiplied by vector of electric field E crossed with the vector of magnetic field B. Typically, we're interested in the average values of Poynting vector S. The average of the Poynting vector S bar is equal to 1/2 epsilon naught c E naught squared, which is equal to 1/2 c over mu naught multiplied by B naught squared. Or we can write it down as E naught multiplied by B naught divided by 2 mu naught. Or we can say RMS value of electric field multiplied by the RMS value of magnetic field divided by mu naught. Okay, let's look at problem number 32 in the book as an example. Estimate the average power output of the sun given that about 1,350 watt per meter squared reaches the upper atmosphere of the Earth. The radiation from the sun has the same intensity in all directions, so the rate at which it reaches the Earth is at the rate at which it passes through a sphere centered around the sun, with a radius equal to the Earth's orbit radius. The 1,350 watt per meter squared is the intensity, or the magnitude of the Poynting vector. So the magnitude of the Poynting vector is power divided by area. Therefore, we can solve it for the power is equal to magnitude of the Poynting vector multiplied by area is equal to 4 pi r squared. Here r is the Earth orbit around the sun multiplied by s. Plug in the numbers. Power p is equal to 4 pi 1.496 times 10 to the power 11 meter multiplied by 100 multiplied by 1350 watt per meter squared. I forgot to square it here. And that simplifies to 3.8 times 10 to the power 26 watt. That's a huge amount of power radiated from the sun reaches to the Earth. Section 9. Radiation pressure. In addition to carrying energy, electromagnetic waves also carry momentum. This means that a force will be exerted by the wave. The radiation pressure is related to the average intensity. It is minimum if the wave is fully absorbed. So radiation pressure, capital P, is equal to force F divided by area A, that is equal to 1 over A, the derivative of the momentum over time, dP over dt. We can write it down as 1 over A multiplied by c, speed of light, multiplied by the derivative of energy absorbed, U, with respect to time. That is equal to the average value of the Poynting vector, S bar, divided by c, the speed of light, when the wave is fully absorbed. The maximum of the radiation pressure is when the electromagnetic wave is fully reflected. So maximum radiation pressure is equal to 2 times S bar divided by c, speed of light. Let's look at problem number 38 in the book as an example. What size should the solar panel on a satellite orbiting Jupiter be if it is to collect the same amount of radiation from the sun as a 1 meter squared solar panel on a satellite orbiting Earth? Assume the inverse squared law. The intensity from a point source is inversely proportional to the distance from the source. So let's write it down. The intensity on the Earth divided by the intensity on Jupiter is equal to 1 over r squared from Sun to Earth divided by 1 over r squared from Sun to Jupiter. And that gives us r squared Sun to Jupiter divided by r squared Sun to Earth. Let's plug in the values, equal to 7.78 times 10 to the power 11 meter squared divided by 1.496 times 10 to the power 11 meter squared, which gives a value of 27. So it would take an average 27 meters squared at Jupiter to collect the same radiation as 1 meter squared solar panel on Earth. Section 10. Radio and television, wireless communication. The figure below illustrates the process by which a radio station transmits information. The audio signal is combined with a carrier wave. So here we have a sound wave from the speaker on a television or radio station talking to a microphone. The audio electric signal goes to an AF amplifier. The audio signal is amplified, goes to a mixer, and is mixed with an RF oscillator, and it carries to a modulated signal as either amplitude modulated or the frequency modulated, goes to an RF amplifier, and goes to an antenna which transmits the wave as electromagnetic wave to the receiver stations. Such a mixing of signal and carrier can be done two ways. First, by using the signal to modify the amplitude of the carrier, or amplitude modulation, as is shown here. So we have the signal we're interested in, and we have a carrier, which is a constant oscillation or constant frequency wave, and it's acting as the carrier of the signal. And we mix these two signals into an amplitude modulated signal. In a second method, by using the signal to modify the frequency of the carrier, or frequency modulation, FM. So the top wave is the program or the audio we want to transmit. We use a carrier which is known frequency and amplitude, mix these two signals in a frequency modulation, and the total signal is a frequency modulated signal and is being transmitted. And this is the total FM signal. At the receiving end, the wave is received, demodulated, amplified, and sent to a loudspeaker. Here we have an antenna which is receiving the wave which we already transmitted from the source antenna and is received by the receiving antenna, is sent to a RF tuner, an amplifier. The RF signal will be demodulated to extract the actual signal which was modulated originally. The signal is now an audio signal which will be sent to an AF amplifier, and that signal is sent to a loudspeaker. We already talked about it. That, by the vibration of a membrane, generates a loud sound. The receiving antenna is bathed in waves of many frequencies. A tuner is used to select the desired one. This is a cartoon of the antenna which received a signal, sends it to a tuning circuit. With the help of a capacitor, we can select which frequency we are interested in, and that signal is being sent into a transistor amplifier, and that can filter out other unwanted frequencies and only capture the frequency we are looking for. A straight antenna will have a current induced in it by the varying electric fields of a radio wave. A circular antenna will have a current induced by the changing magnetic flux. This is a linear antenna, and this is a circular antenna. Alright, let's take a look at problem number 46 in the book as an example. A certain FM radio tuning circuit has a fixed capacitor, C equals 680 picofarad. Tuning is done by a variable inductance. What range of values must the inductance have to tune stations from 88 MHz to 108 MHz? So apparently this circuit is an LC circuit, and the resonance frequency of such LC circuit is given by omega over 2 pi, 1 over 2 pi, the square root LC. We can solve this equation for the inductance. L is equal to 1 over 4 pi squared F squared C squared. C is the capacitance. We're talking about two ranges of frequencies, 88 MHz to 108 MHz. So we have two values of inductance. For L1, for the lowest frequency should be the highest inductance. Should be 1 over 4 pi squared 88 times 10 to the power 6 hertz squared times 680 times 10 to the power minus 9 farad. And that is simplified to 4.8 times 10 to the power minus 9 Henry. The second impedance is 1 over 4 pi squared 108 times 10 to the power 6 hertz multiplied by 680 times 10 to the power minus 9 farad. And that gives us 3.2 times 10 to the power minus 9 Henry. So this is the range of possible values for the inductance. Summary of chapter 31. Maxwell's equations are the basic equations of electromagnetism. The first one is the integral of E dot with dA over the closed area is equal to the charge Q over epsilon naught. The integral of B dot dA over the closed area is equal to 0. The integral of E dot dL over the closed loop is equal to minus the derivative of the magnetic flux over time. The integral of B dot dL over the closed loop is equal to mu naught I plus mu naught times epsilon naught times the derivative of electric flux phi sub E over time. Electromagnetic waves are produced by accelerating charges. The propagation speed is given by V equals c, the speed of light, equals 1 over the square root of epsilon naught mu naught. The fields are perpendicular to each other and to the direction of propagation. Wavelength and frequency of electromagnetic waves are related through equation C equals lambda times F. The electromagnetic spectrum includes all wavelengths from radio waves through visible light to gamma rays. The Poynting vector describes the energy carried by the electromagnetic waves. It's given by S equals 1 over mu naught vector E crossed with vector B.